Okay class. Okay class. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. So today we're gonna continue on another topic. Okay, called stereochemistry. Right. So basically, some introduction. Stereochemistry, a subdiscipline of chemistry, involves study of the relative spatial arrangement of atoms that form the structure of molecules. Okay, an important branch of stereochemistry is the study of chiral molecule. Stereochemistry is also known as 3D chemistry because the prefix stereo means three-dimensionality. The study of stereochemistry focuses on stereoisomer of organic chemistry. So basically, previously we already learned about the isomers, right? And isomers, okay, is the main idea of stereochemistry. And stereochemistry is the subdivision of the isomers. So isomers is the main, and then we have constituent isomers, and then we have stereochemistry, and then towards that we have another different part of isomers. But the initial things, the first thing or the idea of stereoisomer chemistry is isomers, right? So here, okay, here are the isomers. Isomers are different compounds with the same molecular formula. That's the basic idea of isomer. So there are two major classes of isomer, which are constitutional or structural isomers and stereoisomers. For constitutional isomers, they have different IUPAC names, the same or different functional group, different physical properties, and different chemical properties, meaning even though they have same numbers carbon, same numbers of hydrogen, same numbers of atom, but actually they are different compound or molecule. So that's constituent isomer. We will look at some example later. Okay, another thing is stereoisomers. Stereoisomers differ only in the way the atoms are oriented in space. Okay, meaning the configuration. So it very much different about constitutional isomers. Constitutional isomers is very much different about how the atom is attached between each other. So we easily for us to distinguish between in constitutional isomers. But stereoisomers are a little bit difficult for us to imagine because it's related to here. A particular three-dimensional arrangement is called a configuration, and stereoisomer differ or difference in configuration, meaning you have to imagine they have the same numbers of atom, and then they have the same IUPAC names, but the configuration or attachment in the space is different. Okay, in the space is different. Example, we have some telephone here. Okay, so maybe one side, this basically, okay, example, this is A and this is side is B. So basically this two is the same phone, but the way it face you, okay, the front you is different. So that is stereoisomers. Okay, that's the difference in between constituent isomers and stereoisomers. So constituent isomers, they are both different handphone. Okay, so the first one is okay, this one is iPhone, and another one is the same sizes, the same molecule, the same camera in the front, but it look the same, but it's different in terms of uh, brand. Okay, one is iPhone, another one is Samsung or someone, but storage camera is the same phone, but the way it faces you, uh, the way it you look at the phone itself is different. So you will see at the back, you see at the front. So that's different in storage summer. So imagination in storage summers is quite important, right? So here we have some introduction example. So this is example of constitutional isomers. So look at here, they are have the same number of carbon and number of hydrogen, but actually they are different because here there are two metal pentane, another one is three metal pentane. So actually they are different molecule in terms of, actually they are very much different molecule, meaning they have different properties, they have different chemical reaction, something like that. They has different in terms of anything. So basically they are different in terms of isomers. You can see the carbon, hydrogen and hydrogen have the same number, and then we can see the configuration, meaning the configuration meaning the configuration itself is the same, okay, but the difference in cis and trans, because only the difference of cis and trans arrangement, but so there are isomers in terms of stereoisomers. First, we look at the chiral and achiral, which means the most important part in stereoisomers is chiral and achiral compound. So although everything has mirror image, so basically this is some introduction for you to understand what is chiral and the chiral molecules. So although everything has a mirror image may or may not be super impossible. A molecule or object that super impossible on its mirror image is said to be a chiral. A molecule or object that is not super impossible on its mirror image is said to be chiral. Generally, a chiral carbon atom is sp3 with four different attachments. So here, when you look at your fingers, okay, this is your finger, okay, your hand, okay, and then try to imagine you put a mirror here, okay, and then so this will be your mirror image. Is it? This will be your mirror image, okay, like this, okay. You look your hand like this. In the middle is the mirror, is you put a mirror, so this is your original, this is mirror image. So when you put it together, it's not super impossible, so this is chiral. Okay, that's one thing. But when you put your hand like this and you put a mirror here, so it will be your mirror image. So if you put it together like this, right, it will be super impossible, so it is a chiral. Okay, a chiral and chiral. So here's the example, right? This is a molecule or object that is not super impossible on its mirror image is said to be chiral. Okay, some molecule are left hands are mirror image, but they are not identical or super impossible. This is another example. So basically, when you put a, okay, when you put a mirror here, okay, when you put a mirror here, you will see both this one and this one is mirror mirror image. This is the mirror image, and it, when it be super impossible together, it can be attached, okay, each other. However, for this one, this will be in the right hand side, meanwhile in this will be in the left hand side of the chair. So meaning when we superimpose both figure, it will not be super impossible. Meaning that when we put attached to the other, this one will be left one here, and this one will be looking at here. So it's not the same. So basically, this is a chiral, while this is chiral. Okay, that's the major difference between chiral and chiral. Let's look at another example. So this is a molecule. We have molecule. This is mirror. So this is impossible. This is a chiral. And another example here. This is non-super impossible. So it is a chiral. Okay. So a carbon atom with four different groups is a chiral. So this is the most important statement. A carbon atom with four different groups is a chiral center. That is major, the most important thing. The case of two betanon here. This is example. We look at just straight away. We look at the example. This is the this is the two betanon here. Okay, A is the mirror image. Label B is not super impossible. Okay, it's not super impossible. The two betanon is a chiral, and A and B are isomers. Isomers, okay, in terms of cis and trans, okay, if we call diastroma. Meanwhile, in terms of a chiral, okay, a chiral equal with enantiomers. Later on, we will look at one by one, so easier for you to differentiate between diastroma and enantiomer. Okay, so first we understand first about chiral and chiral. So thus, 2-butanol is a chiral molecule. So non-square image stereoisomer like A and B are called enantiomer. Okay, so let's just look at the first statement here. A carbon atom with 4 different groups is a chiral center. So first you choose your carbon atom that you want to look. Okay, here, this is carbon atom that we choose to see either it is chiral or a chiral molecule. Okay, so then we look at the 4 molecule or the groups that attach to the type of atoms. Basically we call it molecule or groups, functional group that attach to that particular or the selected carbon. So we look at here, we have CH3, the first carbon, and then this two CH3 to A2, and the one EH, the fourth one OH, meaning that 4 different groups that attach to that selected carbon. So basically, from that particularly is a chiral carbon or chiral, which is a chiral molecule, not a chiral, but a chiral. Okay. In general, a molecule with stereogenic or stereocenter, some we call stereogenic, some we call stereocenter. It depends. Will be a chiral. So this is general view. Uh, when we have a stereogenic or stereocenter, so the carbon is stereocenter. The carbon that we choose here, it is a stereocenter. So once we have identified that the carbon is stereocenter or stereogenic, so uh, it will be chiral. With one stereogenic center, a molecule will always be chiral. With 2 or more stereogenic center, a molecule may or may not be chiral. So what are the difference between these two statements? So one stereogenic center, a molecule will be chiral. So we know that organic compound will be one straight or two straight, or which is numbers of combination of carbon. Is it? So like example hexane, okay, hexane which have a number of 8 carbon and so on. So we must look at we must choose what type of carbon that have storage center. Either it is maybe number 1, number 3, number 6. So we can look at the whole center, at the whole carbon, to see either it is a stereogenic center. Okay, and then it is possible that that particular line or that particular molecule have 2 or 3 centers, stereogenic centers, meaning they have the carbon, it is stereogenic, which means there are 4 attachment or 4 different functional group that attach to the particular carbon. Okay, so that's why one molecule can have one stereogenic center and some molecule have 2 or more stereogenic center. So that's the statement here. We will look at some example for your explanation or for your understanding. A chiral molecules contain a plane of symmetry, but chiral molecule does not. A plane of symmetry in middle plane that cuts the molecule in half so that one half of molecule in reflection of the other half. So usually a chiral molecules, okay, and a planar symmetry contain a plane symmetry. So look at the example here, right? So basically, if it's chiral, it can be cut in half of your molecule. It will be a chiral. So basically, that's how you differentiate between chiral and a chiral. A chiral, for chiral, when you put the sum plane here, it cannot be sample like this. Okay, the center is some plane. Okay, the center here is some plane for your imagination. So when you cut in half, it can be superimposed. So it will be a chiral. Okay, a chiral. Right. So this is another example here. 2 identical attachment on sp3 carbon atom eliminates the possibility of chiral center. So CH2 Br Cl. Okay, it can be cut in half. No plane of symmetry. Okay, this is can be superimposed here, right? So that's why it can be a chiral. So when you have plane symmetry, this cannot be superimposed here. Okay, so it is chiral. Okay, that's on how imagination of it. So that's why stereochemistry, not isomers. Okay, stereoisomers needs your imagination. Okay, on how the 3D arrangement of your compound. Right. Basic principle of chirality. The fundamental question is whether the molecule and its mirror image are impossible. When it's related to chirality, the idea is either the mirror image is super impossible or not. Okay, that's the question. When you look at when you look you search for a chirality in some molecule. If a molecule and its mirror image are not super impossible, the molecule and its mirror image are chiral. Okay, the term stereogenic center or stereocenter and chiral molecule are related but distinct. In general, a chiral molecule must have one or more stereogenic centers. Okay, the presence of a plane symmetry makes molecule chiral. So the idea, this is some explanation from this statement. Okay, so this statement here and this statement here are related. Okay, these are idea of enantiomer. So enantiomer, a mirror image, a pairs of compound that are non-superimposable mirror image, which is they contain chiral or stereocenters. Okay, chiral different from its mirror image, having an enantiomer, a chiral, identical with mirror image, not chiral. Meaning chiral will be enantiomer. Okay, we look at example here, a chiral, meaning when we cut in half, this is the mirror image. The mirror image can be impossible. The another different thing, the another difference we can see is when we cut in half, it can be super impossible, and it can be impossible with its mirror image. So it is a chiral. So meanwhile, so this is non-enantiomer. So meanwhile, Cl here, it cannot, when cut in half, it cannot be superimposed. Okay, and it are not superimposed with its mirror image. This is his mirror image. So we have compound A, compound B. Compound A and B we call enantiomer. Okay, enantiomer, remember, enantiomer is they have both molecule. This is chiral, and then this is A and B, they we call enantiomer. If only A is not, we cannot call it enantiomer. Enantiomer contain both non-superimposed image or non-superimposed molecule. Okay, this is some. Okay, we look at another example, the previous example. So this is B is the mirror image of A. They have four different groups that attach to the center that we choose, which is it contain stereocenters. Okay, first, okay. Next, we look at the mirror image. Either it is superimposable or non-superimposable. If non-superimposable, so superimpose, so it is chiral. And then this molecule is enantiomers. Remember, enantiomer must both have A and B. Okay? Okay, stereogenic centers or stereocenters. To locate a stereogenic centers, this is how we determine the stereogenic centers. Imagine, examine, okay, each tetrahedral carbon atom in a molecule. Choose a carbon atom in molecule that you want to predict either it is chiral or non-chiral, and look at the four groups, not the four atoms that bonded to the selected carbon atom. Remember, look at the four groups and not the four atoms bonded to it. Okay, always omit from consideration all carbon atom that cannot be tetrahedral stereogenic center. This includes CH2, CH3 group. Okay, this cannot be stereogenic center because it will be CH2 only and this CH3 is CH2 only. So it cannot be center. Okay, right. So first, this is stereogenic center because they have four different atoms that attach to it. Okay, and this is another stereogenic center because there's four different functional groups, or groups that attach to the carbon. So actually this is different from this. So that's why we call it this is stereogenic center. Okay, larger organic molecule can have 2, 3, or even 100 of stereogenic centers. Okay, basically it depends on, so basically you will be asked how many stereogenic center in that particular molecule. How many stereogenic are possible in cell. So how to determine it? You choose your centers differently. Okay, so here there are two possible stereogenic centers because it the selected carbon have four different attachment. Okay, so how about here? If we choose this is H, this is will be H. So basically there are two same groups that attach. So it will be not strategic center. How about here? It's the same. How about here? It cannot be center because it cannot, it already double bond. And then how about here? It's the H2. Okay, so that's why only two have. So when you selected uh, to look at the strategic center, first choose what type of carbon, or look at the carbon that you want. Okay, is another example. Okay, first must the most important part, or it's easy for you to determine the chiral center. Look at the groups of functional group that attach to that particular carbon. If that particular carbon attached to four different group, it will be chiral. So here they have three stereogenic center. Okay, so drawing stereogenic centers using the wedge diagram. To draw both enantiomer, remember, enantiomer must be A and B. Both when you, if you didn't draw, only draw A is not be enantiomer. Okay, you to make it enantiomer, you have must draw A and B to make it enantiomer. Okay, use typical convention for depicting tetrahedron. So usually this is the way how it will be drawn. Okay, only the difference is what type of functional group will be attached to the particular carbon. Two places to have bond in the plane, here and here. One in the front of plane on a wedge, OH here, and behind the plane OH dash, okay, here. Then to form the first enantiomer, arbitrary place the four, okay, just make it draw like a mirror image. Easy, okay. Draw the mocha. Okay, this another example, bigger example for you. So first, it always will be drawn like this. Okay, okay, because we look at the four different group only. So here will be two in the plane, in the front, and one in the back. So again, look, draw again in the image form. Because this is example, we have an amino acid, and then this is bromohexane. Okay, in trimethylhexane, the CH3 and H written they are above and below the plane of the ring are drawn with wedges and dashed as well. So this is for you to draw in terms of different uh, in a cyclo. Okay, so when you look, when you put a plane here, in here cannot be superimposed. Something same again here. So it in the chiral center here, they have four different that attached to it. Okay, so that's why it become a chiral. It become chiral here. Okay. Okay, labeling stereogenic centers with R and S. So there is a way for us to show it R and S. Okay, since enantiomer are two, so A, we cannot say it A and B. So it's impossible. Just example. So to look at the A and B, so we'll put R and S to differentiate between these two enantiomers. Since enantiomers are two different compounds, they have to be distinguished by name. So it can be added R and S. And enantiomer prefix R and S is called Kahn-Indoor Prelog system. To designate the R and S, priorities must be assigned to each group bonded to the strategic center in order decreasing number. Okay, the atomic highest number, this is important, the atom of highest atomic numbers get the highest priority. So we already know the center, and then we look at on how to differentiate the different in any, we must look at a different idea. Okay, bromine, we have hydrogen, bromide, fluorine, chlorine. So the highest atomic number is bromine, hydrogen, fluorine, and chloride. Okay, so if two atoms entering the center are the same, assign priority based on atomic number of atoms bonded to this atom. On one atom of high atomic number determines the higher priority. Okay, so if two atoms on stereogenic center are the same, meaning here C, C. So we look at the next attachment to me, right? So there possible that this can be 2, can be 3, can be 2, can be 3. This will be number 1, this will be the lowest. The problem is which one is number 2, which one number 3, because the carbon attached to the carbon. So it's the same. So to look at it, look at this next particular carbon, okay, attachment. So this will be number 2 because the C will attach here, and then it's only hydrogen that attached to number 3, so it will be number 3. So the configuration will be 1 2 3 4, right? So okay, here it's quite easy. Okay, bromine, chlorine, right, bromine, chlorine. Okay, bromine, chlorine. Okay, sorry. Right, we continue. Okay. Uh, okay, this example, the bromine, chlorine, carbon, and hydrogen. One, two, three, four. So it's easy for you to look at a different item that attach or functional group that attach to carbon. But the problem is when almost the same carbon that attach to the same carbon that attach to that particular carbon. Okay, this is C, 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 C. So it's quite almost the same. But important things is next to look at how the attachment. Okay, this is A2 attached to the C. So C, C here. Okay, two number C, and then the one H H C. The number 3 because the number this number is higher, and this is 1 1 2 3 4, and meanwhile this is 1 2 3 4. Okay, this is how you assign number. Okay, this is important because you want to look at the rotation, which one is number 1, which one number 2, number 3. Okay, so how to assign RNS? So to assign RNS, you cannot assign directly by this particular drawing. Important thing, the most important thing, stereoisomers must be configuration in 3D. Okay, so to label R and S, you will look at the A and B, two enantiomer multiple. Okay, how to assign R and S? Okay, first numbers the priority. Okay, OH will be number 2, 1. Okay, number 1. So CH3 number 2, CH3 number 3, number 4. Okay. Okay. Step 2, how to look at the rotation. Okay, ada R, OS. Okay, first put group 4 at the back. So we will look, okay, here. Okay, sample like this. Okay, okay, look at the back. So you will see, or you will look at number 1, number 2, number 3 only. Okay, when you put it 4 at the back, so we look at number 3. So at the end, this is how, and then the rotation is here. Okay, when you look at enantiomer B, okay, the mirror image, okay, look at the, put the number 4 at the back, and then we look at here. Okay, so you'll know the rotation. So in terms of rotation, R will be clockwise, meanwhile S will be counterclockwise. So here we related to the R, to related to S. So that's how you determine, differentiate between the R and S. You cannot label A and B, so you will know that R and S isomers. Okay, it's all right. So the idea is, you must try and able to imagine the 3D structure of the selected compound or selected molecules. Okay, you must imagine how the arrangement of the particular molecule in terms of attachment to that particular or selected stereogenic center. Okay, this is another example of the Lewis parity and how to RNS. Okay, RNS assignment in compound in two or more stereogenic center. It is important because you will know that that particular molecule can remember that that particular molecule can have one or two stereogenic centers, can have three stereogenic centers. So you will able for us to look at this as this C, which is S configuration. So in that particular, it will have R and S configuration. Okay. All right. In we look at another example. Okay, diacetyl cycloalkanes. Consider 1,3-dimomocyclopentane. Since it has two stereogenic centers, it have maximum of 4 stereoisomers. Okay, this is stereogenic centers. It can be diastromers. What is diastromers? Enantiomer is isomers have that have stereocenters that cannot be superimposed. But diastromers is stereoisomers, okay, that can be superimposed. But the difference is diastromers it's easier for you to look at the cis and trans isomers. Okay, that's the difference between diastromers and enantiomers. Okay, so okay, here how we differentiate between isomers and so on. So the main particular or the parent or the idea is the isomers, different compound with the same molecular formula. So it can be divided into two constitutional isomers. Constitutional isomers have different kind. They are different molecule, but they have numbers of carbon, the same number of carbon and hydrogen. So that is constitutional isomer. Actually, they are different molecule, but in isomers, which is quite different. Okay, it's the arrangement of their atoms in space. That's the difference. So enantiomer, stereoisomer that are F2 enantiomer, which is non-superimposable. Meanwhile, diasomer are mirror image and can be superimposable. Okay, this is some example. We have molecular formula, these constitutional isomers. It can be butane, it can be isobutane, meaning they are different molecules or molecule or structure. Okay, for enantiomer, they are non-superimposable of their mirror image. Meanwhile, diastroma were related to the cis and trans. They are okay. Okay, that's the difference. Okay, mirror image molecule have nearly identical physical properties. Okay, so we look at the enantiomer activity. So why the importance of enantiomer? Why the differences in stereoisomers? Okay, in stereoisomers, different with constitutional isomers. Constitutional isomers, actually they are both different molecule. They are both different molecule, meaning they have different properties and so on. Unlike stereoisomers, they have the same properties exactly. Mirror image molecule have nearly identical physical properties. The example are okay, color here is most the same. But enantiomers show different behavior only when they interact with other chiral substances, including their own enantiomer. That's, we can say, the most or the important idea of enantiomer. So it will not affect in terms of its physical properties, but it will different in chemical properties. It meaning it will different in reaction, type of reaction, the product, okay, it will be different. So that's the important in enantiomer. Okay, so we have the most important part or the most idea of enantiomer is optical activity. One easily observable way in which enantiomer differ is in their behavior towards polarized light. When a beam of polarized light passes through an enantiomer, the plane of polarization rotates. That's the we can say the quite nice or quite uh, distinguished properties of enantiomers. Separate enantiomer rotate the plane polarized light equal amount but in opposite direction. That's why we have R and S. Okay, clockwise and counterclockwise. That's why the rotation is different, so it can rotate the plane polarized light. Okay, separate enantiomer are said to be optical active compound because of their effect on plane polarized light. Okay, so enantiomer also we can call it optical active compounds. Okay, biological, another idea of enantiomer in terms of biological activities, differences, reaction in biological field. Biological system commonly distinguish between enantiomer. They can distinguish between enantiomer. Two enantiomer may have totally different biological properties. Enzyme in living system are chiral and can distinguish enantiomers. In general, just one of enantiomer produces the characteristic effect. The other either produce no effect or has no as a different effect. Meaning R and S has different reaction or different idea, different reactivity in terms of biological activity. Maybe the another one that we want, the other one is didn't contribute at all. So that's the differences between enantiomers. So this is example. This is R epinephrine and S epinephrine. So this is R rotation and this is S rotation. So in biological system, which is enzyme, so basically this R is active site or active enzyme. Meanwhile, for the S is non-active. So in that particular reaction, on that particular biological effect, we only want R rotation epinephrine. Okay, that's the differences. Okay. One more thing is our nose is also capable distinguish some enantiomers. Example is R carbon and S carbon. R carbon is the fragrant associated with spearmint oil. Okay. Meanwhile, the S carbon, the tangy odor of caraway seed. So you can see these both molecule are the same molecule, but the configuration of this molecule in 3D system are different, are very much different. That's why this idea, they affect the reaction, but in terms of physical properties, in terms of boiling point, in terms of melting point, both R and S is same, but in terms of reaction, chemical reaction, it we can say it's look like different molecule. So that's is the differences or distinguish idea between enantiomer in enantiomer. So I think that's all. Thank you very much. So if you have any question, okay, if you have any question, you can ask me anything. All right. So I hope uh, everyone is doing well, and please ask me if you have some question. If not, that's all from me. Thank you very much.